Welcome along to this deep dive. Today, we're tackling something pretty fundamental in pharmacology, really crucial if you want to understand how a lot of medicines actually work. We're zooming in on molecules that, well, they don't cause an effect themselves. Instead, they block the effects of other molecules. We're talking about antagonists.
That's right. We're drawing on some great material from Dr. Junaid's lecture to help us.
Yeah, excellent stuff. So our mission today, let's really unpack what antagonists are, get into how they work at a molecular level.
And crucially, why the different ways they block receptors matter so much.
Mm.
Both for researchers in the lab and for doctors treating patients.
Right. It's like if you think of an agonist as the key that fits a specific lock the receptor and opens a door, triggering some biological response.
Then the antagonist is something that messes with that process. It might jam the lock so the key can't turn, or maybe block the keyhole entirely.
Exactly. But it's not just one way of jamming it, is it?
Not at all. That getting in the way, as you put it, happens through several distinct mechanisms. And that's really what we need to dig into.
Okay, sounds good. So let's start with the basics then. What exactly is an antagonist and why should we, care so much about them?
Fundamentally, an antagonist is any substance that binds to a receptor, but doesn't activate it. It just sits there.
Occupies the space.
Right. And by doing that, it prevents the actual agonist, the molecule that should be causing a response, from binding and doing its job.
And the source mentioned something about intrinsic activity.
Ah, yes, very important. A pure antagonist has an intrinsic activity of 0. Binding happens, but absolutely no action follows from the antagonist itself.
So they're completely inert in terms of triggering that specific receptor. Their power is purely in blocking something else.
Precisely. And that blocking ability is incredibly useful. Think about lab research scientists use antagonists like molecular off switches.
Off switches.
Yeah, to figure out what a receptor pathway actually does. You block it with an antagonist, see what processes stop or change. Helps you map out the whole system.
Kind of like pulling one fuse to see which lights go out in the house.
Exactly like that. And then clinically, well, antagonists are just vital. So many conditions involve pathways being overactive, maybe driven by your body's own natural agonists like hormones or neurotransmitters.
Okay.
Antagonists let doctors damp down those signals, block the unwanted effects. Beta blockers are the classic example mentioned in the source.
Right. For high blood pressure, heart conditions, blocking adrenaline, basically.
Correct. They stop adrenaline binding to its beta receptors, which, slows the heart, lowers blood pressure. So, yeah, from basic science to common treatments, antagonists are absolutely key.
Okay, so bind, don't activate, 0 intrinsic activity, crucial tools. Got it. Now, the source starts categorizing them based on how they interact. How do we break that down?
The main split, the first big division, is based on their mechanism. Are they competitive or non-competitive?
Competitive. Okay, that sounds like they're fighting for something. What's the competition?
They're competing directly with the agonist for the very same binding site on the receptor. Usually that's the main active site, the spot the agonist needs to trigger the response.
So first come, first serve for that prime spot.
Or, whoever has the bigger numbers can win out sometimes.
Yeah.
But yeah, occupy the spot, block the agonist. Simple strategy.
Okay. But then the source breaks competitive down further into reversible and irreversible. What's the difference there? Is it how strongly they bind?
Exactly. It all comes down to the type of chemical bond they form. Reversible competitive antagonists. They use weak, non-covalent bonds.
Weak bonds. Like hydrogen bonds. Van der Waals.
Those kinds of forces, yes. Think of it like using sticky notes. They stick, but they're not permanent.
Sticky notes, meaning you can peel them off. Or the agonist can, if there's enough of it.
Precisely. Because that binding is weak, it's temporary. If they will flood the system with enough agonist, the agonist molecules will eventually just outcompete the antagonist for the binding sites. The effect is surmountable.
Surmountable. So if we think about a dose-response curve, you can still get to the maximum possible effect, the Emax.
Yes, you can.
But you need more agonists to get there, so the curve shifts.
Exactly right. The Emax stays the same. You can eventually activate all receptors if the agonist concentration is high enough. But the ECO, which is the concentration needed for half the max effect, that increases. You need more key molecules to overcome the blocker.
So the curve moves to the right but stays the same height, a parallel shift.
The classic picture, yes. A rightward parallel shift. The source mentions naloxone, used for opioid overdoses, as a perfect example. It competes reversibly at the opioid receptor.
Okay, reversible competitive. Temporary binding, surmountable, shifts right. Got it. What about the irreversible ones? Are they like super glue instead of sticky notes?
That's a pretty good analogy, actually. They form very strong bonds, often covalent bonds, right at that same active site.
Covalent. Those are strong. Permanent, basically.
For the life of that receptor molecule, effectively, yes.
Ugh.
Once that antagonist binds irreversibly, that specific receptor is just taken out. Can't bind the agonist anymore, or at least can't be activated by it.
So you can't overcome it just by adding more agonist.
So the effect is not surmountable. Doesn't matter how much agonist you pour in, those receptors that are covalently bound are just gone from the pool of functional receptors.
Okay, so if you're losing functional receptors, that must affect the maximum response, right? The Emax.
Absolutely. Because you have fewer working receptors available, you simply cannot achieve the same maximum response as before, no matter how much agonist you add. The Emax decreases.
The curve gets squashed downwards.
It flattens, shifts down. Phenoxybenzamine, which blocks alpha-1 adrenergic receptors, is the example given. It binds irreversibly.
And what happens to the ECO, the potency measure in this case?
Well, that's a bit more nuanced. It might actually look unchanged at first, or even increase slightly. It depends on something called spare receptors.
Spare receptors, you mean like the cell has more receptors than it strictly needs to get the job done?
Exactly. Some systems have a receptor reserve. If you have, say, 100 receptors, but only need 50% occupancy to get a full 100% biological response, the first 50 receptors blocked by an irreversible antagonist might not lower the Emax.
Ah, okay, so you're knocking out the spares first.
Right. In that initial phase, the curve might just shift rightwards a bit, looking like a competitive effect. Because you still have enough receptors left to reach Emax, you just need more agonists to hit them. But once you block past that spare capacity,
Again, the Emax has to drop.
then the Emax inevitably falls, and the curve flattens downwards. That loss of Emax is the hallmark of irreversible competitive antagonism, eventually.
Okay, that makes sense. So competitive antagonists fight for the main spot. Reversible ones are temporary blockers, shift the curve right. Irreversible ones are permanent blockers, reduce the total receptors, flatten the curve down. What about the non-competitive guys? How do they work if they're not competing for the same site?
Right, so non-competitive antagonists, you'll also hear them called allosteric antagonists or sometimes allosteric modulators. They play a different game. They bind somewhere else on the receptor molecule.
Somewhere else, not the main agonist binding site.
Correct. They bind to what's called an allosteric site. Think of it as a secondary docking point, away from the primary active site.
Okay. But if they're not physically blocking the main site, how do they stop the agonist from working?
By binding to that allosteric site, they trigger a change in the receptor's overall three-dimensional shape, a conformational change.
They warp the receptor.
In a way, yes. This change alters the structure or the environment of the main agonist binding site, or maybe the machinery that connects binding to response. So even if the agonist can still bind to its site.
The lock is warped, so the key doesn't turn properly anymore.
That's a great analogy. The agonist binds, but the receptor just doesn't activate, or activates much less efficiently. The signal doesn't get through properly.
And can you overcome that by adding more agonists?
No, you generally can't, because the problem isn't competition for the binding site. It's that the receptor itself is functionally impaired by the allosteric antagonist. So, like irreversible competitive antagonists, their effect is typically not surmountable. Okay, let's unpack this. We're talking positive and negative allosteric modulators, PAMs, and NAMs, and specifically how they affect the maximum response, what pharmacology calls Emax. Okay, so let's start with the positive ones, PAMs. Based on your sources, if a PAM is there, what happens to the receptor's top potential?
Well, with a PAM present, it's like that stagehand is making the stage better, amplifying the performance. The PAM itself doesn't usually switch the receptor on, but when the main signal, the agonist, is there, the PAM makes the agonist better at doing its job, and often this means an increase in Emax.
Is an increase?
Yeah, the receptor can now hit a higher maximum effect than it could with just the agonist alone.
And your sources bring up a really interesting classic example. Diazepam. I think most people know that name.
Right, diazepam. It's a PAM at the GABA receptor. GABA is our main inhibitory neurotransmitter, sort of the calm down signal. Now, GABA on its own causes a certain level of inhibition, but add diazepam binding to its allosteric spot on that same receptor, it makes GABA much better at opening the channel.
So the maximum effect gets stronger.
Exactly. The maximal inhibitory effect GABA can produce is significantly boosted. The whole system becomes more sensitive, more powerful in response to GABA.
Got it. So PAMs help the main signal reach a higher peak response. They kind of turn the maximum volume UP.
Precisely. It's not just about needing less drug for an effect. They can literally raise the ceiling of what's possible.
Okay, so if PAMs turn the volume up, what about the negative allosteric modulators, the names? What's their story?
Unnames, well, they bind to an allosteric site too, but they do the opposite. Again, they don't usually do much on their own. But when the agonist is present, a name binding reduces the agonist's ability to produce an effect. Its efficacy goes down.
Reducing efficacy, so that means the Emax.
The Emax is lowered, yeah.
Yeah.
The peak response the agonist can achieve is dampened. It's less than what the agonist could manage alone.
And the source material connects this to cannabidiol CBD, which is very relevant today.
Yes, exactly. CBD is described as acting as a NEM at the CB1 receptor. CB1 receptors are usually activated by our body's own endocannabinoids, or say, THC from cannabis. If CBD is present, it makes those activators less effective at stimulating the CB1 receptor.
So it lowers their peak effect.
CBD essentially dials down the maximum potential effect that THC or our own endocannabinoids can have there.
Okay, so let's try and bring this deep dive together, drawing from your sources. PAMs and NAMs are really interesting. They work off stage in an allosteric site. PAMs boost the maximum possible effect. Emax goes up, like diazepam helping GABA.
Right.
While NAMs dampen it, Emax goes down, like CBD reducing CB1 activation peaks. It's a way to sort of modulate the intensity, not just switch things on or off.
Exactly that. It offers this really nuanced level of control over biological signals. It's not just binary, on-off. It's about adjusting the system's capacity.